Hello and welcome to a kind of follow-on discussion around Module 2, where we talk about neural network algorithms. So to kind of revisit this, we talked a little bit about it last week in our Thursday call, but I thought I'd go through it in more detail this time. So this is all about understanding the idea that we train neural networks based upon data that we've previously seen. So they call it observational data training process here. That's really nothing more than you have a labeled data set that you've captured from some process that knows the answer. So you know what something is based upon not just the features, but there is an assigned classification or class that you're aware of. And at the end of the module, you should be able to talk about what convolutional neural networks are, which is, as we talked about in the past, a way of handling complex data, kind of viewing it almost in a three-dimensional way. And you do that by basically having a window of sorts that you move across the data points. And then you should be able to talk about the results that occur during each process, each step of the process. So going back to discussion of what is a neural network, right? So as we talked about before, you have input. In this case, it's blue on the screen. That's essentially going to correspond roughly to the features that you're interested in. You're going to have a hidden layer that's on the screen is red. There's going to be a varying number of those, typically more than there are inputs and more than there are obviously outputs. But there can also be multiple hidden layers as well. In this case, there's a single hidden layer. If there's multiple hidden layers, then we'll typically call it a deep neural network. The circle represents essentially a neuron or a node. Those two terms here are often used interchangeably. The distinction being, I guess you could say a node is part of a layer. A neuron could stand by itself, although it wouldn't be terribly useful. And again, I hit the wrong button. So the 5 basic steps of a neural network, or kind of the processes or the elements, if you will. There's neurons, as we just talked about. That's something that's used to try to classify or do a regression to essentially fit some sort of complex set of data that comes in. There's the concept of value of information. Hey, John. I see you just joined. Okay, I'm not hearing you, so, oh, there you are. Hey, John. So I was just going to run through quickly Module 2 again as a refresher. And if you've got any questions, we can go ahead and start with those. Anything top of mind? Can't hear you. You must be mute, maybe. Still can't hear you. Lovely technology. Maybe a good old textual chat to the rescue. Okay, so I'll go ahead and kind of run through this quickly. We talked about, to revisit a little bit, the concept of a typical pattern of a neural network. You have input, you have a hidden layer, you have output. If there's more than one hidden layer, we call it a deep neural network, just because, more than one is deep. The basic idea here is that typically the inputs correspond roughly to the classes or sets of features that you're interested in, although may not always. There's almost always going to be more hidden nodes in the hidden layer than there are in the input and the output. There could be any number of them depending upon the complexity, both layers and the number of nodes in a given layer. The 5 basic kind of elements, the neurons, just talked about that. The value of information is kind of the input that's going into it that's used to adjust the weights, and essentially kind of corresponding goes with the activation function or the synapse. The concept of a coupling, which basically just means that we include both the inputs times the weights, and then typically add a bias. so that it can make the node behave as we wish it to. Then the output is what you get out of it once it's done its thing. And then generally there's a sequence of these things that flows forward and then generally flows backwards depending upon the type of network. If you're doing back propagation, you're going to take the error and essentially back propagate it, so send it back through so that you adjust the weights. We call that entire process an epoch. Whenever you do that on every bit of data in a training set, once we've done that, then you can essentially assess the accuracy using your validation data set to see how good you're doing to determine if you should keep going or not. Another way of kind of looking at what we just talked about, you get a couple inputs, you get some weights, and then you got a bias. And it's basically as simple as weight times input plus weight times input 2, and then you add those up to do your bias. Very similar to kind of the concept of moving a line on a XY coordinate system. Convolutional neural networks, the background, it did come kind of from how we think the visual cortex works. Probably isn't really how it works, but it's how we think it works. And it's basically to use to find edges, corners, and so on by using what's essentially a sliding window approach in essentially 3 dimensions. This is a simplistic way of looking at it where you're basically sliding it across the image, but that's really what it's about, is trying to find things. And this turns out to be really well for visual stuff, especially recognizing images, patterns, and so on. So I'm going to try again with a demo. A couple of them didn't want to work because sometimes their examples are kind of tied to particular versions of stuff, and so if you do an update, then it stops working, which is always a joy. This works. It comes straight out of TensorFlow.org's tutorials on images. I'll go ahead and try to make this a little bigger and paste that URL into the chat because it's much more useful if you can go take a look at it if you're so inclined. And what did I just do? Go away. Come back here. There we go. Hopefully that went. Not sure it's going through. Kind of weird. Anyway, I can post that up in the group or in the room as well. So go ahead and make it really huge here so you can see it. And made it big enough that the toolbar gets in the way. There we go. So tensorflow.org/tutorials/images/CNN. And that gives you a pretty good sort of demo of using this to the concepts of a convolutional neural network. What's cool with that is that you can actually run this stuff not just inside of your own environment, but you can also run it up in, let's go here, inside of things like this Colab, running Google Colab or tensorflow.org. So, did my network drop? No? Try switching networks. Maybe that'll help. Hopefully I'm back. And video. is not being recorded. Oh, this is one of those days, so I'm going to exit out of this and come back in. Must be something else going on, so I'll just soldier on, and so we can rely on the recording, which that screen is not terribly useful. So jumping back into it, alright, let's try this again. Alright, sorry for the interruption, but some sort of multiple network issues, it appears. So, hopefully you can hear me. Try this again. Any better? Are you there, John? I think WebEx must be having some challenges this evening. Okay. You want to try to talk again and see if we're working? Yep, still not working. Joys of technology. So, sorry for the interruption. Network stuff going on. I'm not too sure where it's at, but anyway. So this is the page. Hopefully you can see it. That I was talking about, tensorflow.org/tutorials images CNN. And what's cool about it is it does give you the choices here to run in Collab or to download the notebook, which is what I've done. So Google Collab, pretty cool technology and environment. I kind of like running things locally, just being me. So that's what I've done here is I've downloaded the notebook. And it starts off as it always does. I'll go ahead and restart the kernel and clear all my output so that you can see there's no smoke and mirrors going on. You start off, as always, by doing an import of TensorFlow, generally as TF. And also, typically you pull a few things in from Keras, which is kind of a cool framework in that it allows you to have multiple backends, or different backends. Maybe not multiple is the right word, but different. So you can run it against TensorFlow or some other framework if you were so inclined. So we start off by making sure we download these images, which are essentially a series of 60,000 images, and it's smart enough to not do it more than once because I've already done it in the past. Then you can go through and do some verification of the data, just grabbing 25 images off of the randomness, essentially. So you're grabbing 25 images and taking a look at them. Not the highest resolution, you'll see. And that's an interesting thing to keep in mind with this kind of work, is sometimes what you end up doing is actually significantly downscaling the image. So we think naively that high resolution is better, right? So why would I want something that's clearly very low res whenever I can have something that's 4K or something, right? And this is kind of in that realm of reducing dimensionality, right? You actually kind of scale it down to where it's much simpler, much smaller, and that's what we typically do work on. We rarely do it on as high of resolution as you can get, which is always counterintuitive. Sometimes you'll even also do things like convert it from color to grayscale, because sometimes we do better with grayscale than we do with color. So here is kind of again a key kind of pattern you'll see, and we're constructing a model, a sequential model, by adding what are essentially layers on top of it. And we start off with the input layer. We're specifying an activation function, and then kind of you're basically saying kind of what it is, right? And you'll notice there's this pattern that's also a forming of conv 2D, so a convolutional two-dimensional. Then there's usually this max pool, then another convolutional, then another max pool, and then a final convolutional. That pattern shows up a fair amount whenever you're doing convolutional neural networks. It's kind of the pattern that you'll see. And so we can go through and take a look at the summary after we've constructed it, and it's just telling us pretty much what we just saw. And again, you can see that the shape here is pretty small, really. I think it's 30 by 30, which is about what that looks like, right? So pretty small. And then you typically next go through, do some more things to the model. We're flattening and we're making it dense. And again, we can now take a look at the summary. Flattening the output, making it dense, and so on. This is where we're getting basically it ready to come out of the end of the process. Then you run it through this compile phase, and that's basically doing kind of what the name implies, taking it from essentially the layers that we've outlined, and essentially turning it into something that can be ran. And then we're actually running it here by calling model.fit, just as we call model.fit whenever we're typically doing classification problems and so on. So very similar sort of pattern. And you give it the training images along with the labels. We tell it how long we want it to run, so how many epochs. In this case, it's going to run for 10 epochs. And then we give it where the validation data is, and that's how it's able to give us the validation accuracy at the end of the epoch. And you can see that it didn't do terribly great after the first epoch. It's slightly better than random, right? But we are improving with each one of these epochs, which is what you would hope to see. A bit of trading off between that loss function and the accuracy of both the accuracy on the training data itself and then the validation accuracy, which is that third set of data we set aside just for that purpose. So unlike test data that the model should never see during training, it's okay to show it the validation data, because that's pretty much all it's being used for, is to determine how well we're doing. And so in general, this is a general pattern as well. You let it run. Likely 10 epochs was not picked at random. That's probably when we'll do pretty well. But you can see that it's considerably improving on each iteration, although 4 to 2% roughly as it runs on the validation set as well. So we are into the sixth epoch, and you can see on the model accuracy on the training data, it's actually doing fairly decent. It's working its way up from pretty much just above, or actually worse than random, to we're now up to roughly 72% accuracy. And so probably we'll do reasonably well whenever we get up after like 10 epochs. The thing to always understand with this sort of approach, you're going to be wrong some of the time. The model is never going to be 100% accurate. You have to make sure that whatever you're using it for, it's good enough, and that's one of the challenges with these sort of approaches, is making sure it's good enough. You don't want to get it to be too good, because there's a point here you're overtraining it. You're basically going to make it fit the training and even validation data pretty well, but when you throw it test data that it's never seen before, it won't do nearly as well. So we're up to roughly 75% accuracy and 69% validation accuracy. And so those two numbers are kind of what you typically will use a fair amount. you're also going to keep an eye on the loss function. You don't want it to be where you're losing it gets too small. It's taking roughly 20 seconds an epoch, so it's just about done. Probably exciting as watching paint dry, but hopefully you get the idea. And then the next step will be to go through. So we finished up validation around 70%, and the accuracy on the training data is 78%. So that's a reasonable sort of thing. You're going to be right most of the time, but you're certainly not going to be right all of the time. And so we can see here the plot of accuracy versus the validation accuracy, and you can kind of get a sense there that if you're not careful, you could be overtraining even at this point. You're starting to see a dip in the validation accuracy. So looking back at this, you can see right in through here, after about the 7th epoch was the one that actually on the validation set was the best. So could be a little bit of overfitting going on already. And then here we can print out the test accuracy, so it's right around 70%. So not too bad, but a pretty good start. Any questions? And apologies that you may have to type them. Okay. We'll do a similar exercise. Feel free to type it if you come up with it later. A similar exercise with the smile detector. Again, this is coming out of a book. We can take a look here. It's out of Advanced Machine Learning Models. Hold on. I guess it's not out of that book. That's the location inside of here. I'll track down the chapter that it's out of. But basically the idea, it's probably out of practical machine learning, which is one I go to a fair amount. So here's a similar sort of approach. You'll notice that we're importing roughly the same stuff. Let me go ahead and restart the kernel and clear the output so that no smoke and mirrors. So taking a look at what we're importing here, the normal sort of characters that we do, some of them, NumPy, Matplotlib, and then we pull in sequential out of Kiera's, dense, dropout, flatten out of layers, as well as conv2 DD, and max pooling 2D. So similar sort of characters is what we did on the last example, and of course it's not going to work. All right. That's how this goes. It worked earlier, so maybe something I installed broke it. I can try to fix that, or probably better use of the time is to talk about the deliverable 2. Unless there's a question. No. So deliverable 2. Again, this is a little interesting because you're creating training materials about how to do data science training using observational data. So you're to design a set of training materials that would be administered to train staff on how you do training. So you're the chief of this data scientist, or you're the chief data scientist for reliable dynamics. You do stuff with robots and manufacturing. You want to train your staff on how to do convolutional neural networks. So the training that you develop will cover all aspects of the observational data training process. This is one of many processes that your company uses to teach its robots how to perform various tasks. The observational or example data is historical data that contains input features that align with various situations and output features that depict what was observed. So again, you're creating training materials, so a training program, so that you can teach people basically how they go through, what are the steps that are involved in training a neural network, and list each one of those steps. And probably the steps that are in this example are pretty good starting place for that, because especially when we talk about convolutional neural networks, they all look a lot like this. You start off obviously with some training, some testing, and then you'll typically take that test set and split it again into a validation set and a true test set. Then you'll do some data exploration. Then you set up typically these layers. It's kind of a common sort of thing. And then add those ones that flatten it out at the end, so you can get do the flattening and then do the dents, so that you can get the results. Also talk about the difference between training sets and test sets, and probably want to throw in validation sets, because that's pretty important whenever you're doing neural networks. And then talk a bit about what convolutional neural networks are and why we like them. Looks like maybe you called in. Is that?
Yeah, I figured I'd give up on the microphone. I don't know what's going on with that, but this is better, so we can actually talk.
Yeah, isn't technology grand? And then
it's just frustrating sometimes. It's unreliable.
There's something going on with the networks today, that's for sure, because I actually had a blip that shouldn't have happened. So basically, that's pretty much the deliverable 2 is a training a curriculum or materials that typically you would use if you were training people of how to get up to speed on convolutional neural networks and training neural networks in general. So
you're pretty much explaining how they work. It's kind of an extension of the first assignment, right?
Yeah, with a little more drilling into the CNN, right? Because I think the first one was a little more generic in nature, but you definitely want to drill into CNN, and kind of, I would probably, if it were just me wanting to learn about it, I'd want to figure out what class of problems is it good for, what class of problems is it not so good for, and so on.
Yeah. You know, one of the things that I think is interesting, and you'll see when you look at my first assignment, you know, I got myself wrapped around the axle a couple of times on the allegory, you know, between the natural brain and the artificial neural net. One of the things that I think our brains do, and I've read various opinions on this, you know, when you look at something, you kind of multiplex it, right? You digitize it. You form a grid. You pick out the features that help you identify what it is and classify it to be a certain thing. And in the example I made, you know, you take it's a network that's trained to recognize one or not one, number one or not a number one. And, you know, just demonstrate the concept, I split it and then send those, you know, that input to the hidden layer. And then the way the hidden layer responds determines the weight response and whether or not the activation for one or not one trips. When I was drawing the artificial neural network, I kind of put that multiplexing stage in there as a pre-processing step, because in the past I've, you know, needed to do that. Mm-hmm. So I don't know. It's curious how it's like magic. How your brain you see something and you quantize everything, and the closer you look at something, the higher resolution, the more pixels you could use into your input, you know, in your network, and the more generalized, you know, it is. The same, and that really kind of hit me when you were showing the low-res images earlier. It's like you don't always need the most crisp, sharpest image, because that probably introduces noise into the big things that matter, which come through in the fuzzy version, you know?
Yeah, I'm not surfing my phone. I'm looking for a book that I've been listening to. Give me 1 second.
Yeah.
Where was it? Okay, it's I don't know if you've heard of Jeff Hawkins. The book's titled 1,000 Brains. And Hawkins basically is I'm trying to remember what he created. Okay. He's did Palm Pilot. That's what he did. He created Palm. and he left. Basically, he did Palm because he wanted to make enough money that he could do what he really wanted to do, which is study the human brain. And the theory
Yeah.
the theory is that our brains have literally thousands of models running concurrently with essentially
Yeah.
some form of democracy determining what it is we think we're perceiving. So you take you look out the window and you see something, and part of your brain might say, "Oh, that's a cow." Part of your brain might say that's a dragon. Part of your brain might say that's just a bush, and so on, right? And then collectively you come to
Yep.
a determination of what something is. And he uses this concept of, I think it was frames is what he called it, which is essentially nothing more than state, essentially, or a set of values and resulting outputs of those values.
Okay.
So, but it's an interesting idea that for us to do something that models the human brain, we might need to have something that's running literally maybe even millions of models in some sort of a hierarchical fashion, right? And it actually kind of
Yeah.
resonates,
Yeah.
right? Because that's,
Yeah. For me, it does.
yeah. And so that's where this idea that, yeah, you definitely, there's something that you do to that data before you do something with it. That's where you'll sometimes run it through like an encoder, like a one-hot encoder. Sometimes you'll reduce the dimensionality by downsizing it. You might, if you're dealing with audio, you might adjust your sampling rate down from, whatever high fidelity you have. You might even downmix the number of channels to a single channel, right? And the other part that's really weird is
Yep.
you may actually want to introduce noise into whatever it is you're getting, because especially in training, there's this concept of enriching your data by essentially mucking with it, right? You turn
Yep.
your images, you slide them around, you add noise to them so that you cover up parts of things, and so on, because that's kind of what you'll get in the real world is noisy symbols, right? So,
Yeah. Yeah.
but yeah, you're right.
That's fascinating.
There's definitely a pre-processing phase.
Yep.
Personally, I think for it to really get interesting, it's definitely going to be in the ensemble approaches, and that's basically what the Thousand Brains is essentially hinting at, is an ensemble approach on steroids, right? Rather than it
Yeah.
being two or three, it's a bunch. Go ahead.
Right. That's really cool.
Yeah, it's and the same thing is, I think to get to be really good with it eventually, it's going to be the combination of the connectionist approaches, various types of deep learning and neural networks. I think there will also be some rules that come to play, and that's kind of probably what they're talking about in Hawkins' approach of a frame. So I don't expect to see a water buffalo on my farm because
Yeah.
I'm not in Africa. I don't, there's the probability of it being here, it could occur, but it's like near zero, right? So,
Yep.
and the same thing with a unicorn. I'm probably not going to see a unicorn on my farm. Not to say they may not they may not exist, but I'm probably not
Never
going to
know.
see one.
Right.
But it's kind of,
Interesting. I'm looking at that book now. I love books like this.
yeah, it's not exactly a light read, but it is quite interesting. I read his earlier, or listened to his earlier one. I forget what it was called, but I've
The old brain.
oops, that's not it. I was wanted to go look at the details so I could get to the author. On Intelligence, I think that was the other one. Yeah, On Intelligence. Similar
That
thing,
was
but
his first one.
yeah, it's kind of where he outlined the theory. This is, or the foundational elements of the theory. This one he's actually trying to tackle kind of how our brain truly works. It's not a trivial topic at all, obviously. And most of the time,
Yeah.
neuroscientists don't even really go into it, right? They kind of stay away
Yeah.
from it. But
They stick to the cause and effect, right? This
Yep.
works to do that.
Yep.
Yep.
And that's where it's interesting, some of the things that they've learned, and I forget the name of his company. They've actually developed some products that are based upon the theories. Part of it is there's a temporal aspect to it as well that a lot of times it gets overlooked. Goes beyond the whole short long term short or long short term memory sort of thing to a whole different kind of level of decay. But definitely some interesting stuff. So I haven't made it all the way through yet, but it's definitely an interesting book and an interesting thing to the topic. Pretty advanced, but still interesting nonetheless.
Awesome. Yeah, very cool.
All right.
Like it.
So I'll get your assignment turned around here probably this evening. And
Yeah, no rush. No rush. I was just thinking about it. Because that pre-processing step and then the post-processing, where you assess the error. Oh, I got that one wrong. Back propagate, adjust your technique, and redo it. It's also similar, to how, I don't know. I just really think it's a really good analog.
Yep.
For what we're doing.
Yep.
So,
yep. Definitely. Yeah, I'm sure you did well. So as always, I guess if you have questions, feel free to shoot me a message or whatever else. And you're definitely on track to wrap this stuff up pretty quick.
Well, hope so. I'm enjoying it. I haven't had an opportunity to really deep dive into neural networks, so I'm reading this book, Neural Networks and Deep Learning, by Charu Agarwal, and he writes pretty well. He makes the topics really easy to understand, and one of the things that really clicked for me in the last discussion you and I had was the output layer is really, an assessment phase where you determine whether or not all the ascertainment in the hidden layers, is adding up to this being classified as what you're targeting or not.
Mm-hmm.
When you sum all those weights as they come in and compare it to your activation function, whatever its shape is, you're going to get different outputs depending on the activation function. That was a big aha for me so far in this one.
Mm-hmm.
So,
yep.
Good stuff.
Yeah, and the aggravating part is that it's not necessarily science. You learn it through experimentation. So there's not a magic always do this sort of thing. Although there's some hints, right? Some commonalities, but there's variations.
Right on. Yeah, I think the architecture of the network is where the art comes in.
Yeah, definitely. All right. Well, I appreciate you joining. It's always nice to have somebody in the room.
Yeah, of course.
And
anytime I can, I will. I saw that we moved Thursday to Wednesday.
Yeah.
That looks like it'll work most days.
Okay, good. Yeah, I was planning to take Thursday and Friday off, but there didn't seem to be an easy way to shift the meeting. And I used to do it on Wednesday anyway, so it kind of is a little more of habit. So just anyway.
Cool.
All right.
That'll work.
All right, sounds good. All right.
Well, thank you. Have a great night.
Yep, you too. Have a good evening. Talk with you on Wednesday.
Sure. Sounds good. See ya.
Thanks.
Bye.
Goodbye.